Hello, team. Looking at Math Connections 11.3. So we are ratcheting through 11.3, Math Connections 1 through 3, 5 through 6. So skip 4, skip 7, skip 9, and skip a couple down the road. Let's take a look at these and see. And don't forget, I did give you one group work, number 1 and number 2. You can choose, working by yourself is fine, but oftentimes working with somebody else will make those go a little bit quicker. But doesn't matter to me. All right, let's take a look. If one angle is obtuse, can another be obtuse? So these are about triangles. All right. And then because I've connected the idea here, I tried to give you one here. Is it possible to have something like this? It may seem like a weird question. Um, the reason the reason why I don't think that it's a weird question, because at the end you might be like, yeah, you can never have that, or you can have that, is because we do geometry on a flat surface. This question absolutely can happen on a globe. So if you think about a globe, this is kind of going to kind of seem a little strange, but the way the globe is designed, if you, let's look at this one. Maybe they can give me a good blow up picture here. Okay. I'm not sure if I'll be able to keep that while I draw with this other device. No, I won't. Okay, well, I'm going to do my best and let's see if it works out. So up here at the top would be like the North Pole, right? So if you walked straight down from the North Pole until you hit the equator, that would be a 90-degree angle. Okay. And then let's just say you walked over across to the tip over here of South America. Okay. And from South America, you walk directly up to the North Pole. Turns out you can walk in a straight line up to the North Pole there, and you can actually have a right angle from there too. Because if you just go, you're going east, you make a 90-degree turn left and go up, you will hit the North Pole. But you already came down from the North Pole. So what we have is on a globe, because if you think about it, it's not a flat surface, it's been pushed out. And because it's been pushed out, you could actually have uh, 3 90-degree angles up here. So on a globe, you end up with 100 and well, typically the triangle is 180 degrees. The globe measure for a triangle is actually going to be greater than 180 degrees. Okay, it kind of like your lips are pushing out on your cheeks. It pushes it out. So it was 180, but now it's pushed it out like that. And you could actually ask yourself, Scott, is it possible to go the other direction too? And it is. So if you kind of suck your lips in or kind of go to the other side of the globe that's kind of pushed out, we get something that's known as a different type of geometry, not spherical geometry. And so that one, the sum of those is less than 180 degrees. So when we're dealing with a flat surface, it will be exactly 180 degrees. So that's why when we're doing these type of questions, I mean, it looks, you're like, what? But there's actually a good reason for it. Okay, let's see here. What else did I say? Oh, skip 4. Yeah, so can the sum be this? And again, there's nothing wrong. I didn't pick all of them because even though they're reasonably good, picking one or the other seems to be just fine. So let's see here. How is angle 4 related to angles 1 and 2? So again, taking a look at this, can you find a relationship between 4 and angles 1 and 2? And this is a very handy relationship to have as you go forward. So I definitely wanted to assign this question because of that. And let's see here. Explain how to find the sum of the measures of interior angles of a convex pentagon by choosing a point in the interior and constructing triangles. Oh, interesting. So we have an approach that the book already did where they said if you had a pentagon like this, right, they would take and go kind of from here to here, then from here to here. That's kind of the approach that they did. So really, you're kind of taking the lines from one and forming these, and then you just count how many triangles are made. That's one approach. The other one is to start here in the middle, any point in the middle, and kind of go to the outside and then count how many triangles you make, but realize you might have had a little extra in here because you did, all those angles do add up to something. So see if you can make that connection. I think that's also, it's cool to see sometimes that you can get to the same place without the same formula. or with a much different approach. Okay, I skipped 7. I do 8, then 10 and 11. So now all of those were for convex shapes. Now we're going to ask you to do a concave shape. So the question once again is, find the sum of the measures of the interior angles of this one. It is not convex. So I can't do the same like what the book was doing previously, what the authors were saying. They'd say, from here, draw to the vertices. And the problem is that this triangle is outside. So it's outside of the shape. So I can't use that same approach here if it's concave. So think about that as you do it. Let's see here. I think I did 10 and 11. So these are kind of fun as well. The light beams kind of reflect around. Very handy tool. So that is 10 and 11. And this works. Yeah, I guess it's kind of fun to see in my mind. So you see this beam of light comes in, it reflects. And what you get to see is when it does reflect, it bounces in a very specific way. So angle 1 and angle 2 are actually the same measure, which is kind of cool. And angle 3 and angle 4 are the same measure. That doesn't mean that 2 and 3 are the same. It just means that 3 and 4 are the same. Okay. And what you can kind of see is if you did have mirrors lined up and the mirrors were perpendicular to each other, the light would bounce off and go back in the direction, kind of in the direction that it came from. This also holds true on like a pool table. When you hit a pool table, like the ball bounces off as it hits, as long as the wall is flat, it's going to bounce off and hit with the angle of incidence. That's the name, is like this created the situation. Angle of incidence and angle of reflection. So we have those. Oh, let's see here. What else did I assign? 8 through 10, I said 15 through 17. So skip those, and here we are. Questions in the classroom. Jan wants to make tiles in the shape of a convex polygon with all interior angles acute. Okay. So she wants all the inside angles to be acute and wants to make a convex polygon. Now remember, convex polygon, key term, and also, so not concave, it's convex, and wants to know how many times that can happen. Okay. And then, is there a convex decagon with exactly 4 right angles? Interesting. Decagon, remember, we're using terms. So decagon, 10, like decade, 10 years, and wants 4 right angles. So you can build yourself a decagon. Just remember, if you're building it, don't put the 4 right angles like all right next to each other, because it would kind of bring you back almost to like a square. So, okay. And student wants to know if a triangle can have 2 right angles. Again, links back a little bit to that one on the previous page, but that one was using exterior angles, and we want to use interior angles now. Okay, so that is the kind of the big pieces. I think I will try to do one of our activities when we get into using the computers and the different projects. We can kind of see what does it look like, and one of them is really cool as you kind of project where the ball is going to go. You can kind of, when you're playing pool, sometimes you'll see people kind of lay their cue up against the edge from the ball, kind of making an angle. And what they're doing is they're saying, if I hit the ball right here, right, then this angle will be formed. So if you take that angle and you reflect it off, you can see where the ball is going to go afterwards. So that's pretty cool. All right. Ooh, that's it. Oh, and I did say GW1 and 2. Let me take a look at those. Sorry, I was going through them a little too quick. GW1 and 2. So GW1 and 2, group work. So you just turn the page and you'll have some group work here. So group work here is kind of finding something called angle bisectors. And again, the line right now, we're not creating or controlling them. We're just saying they exist. And so I'm asking you something. If the measures of A and B are known and you have the angle bisector, then the measurement of angle D can be found. How can you find angle D if all you knew was A and B? And suppose angle A and B are not known, but you do know angle C. How can the measure of angle D be found? So again, you know C. You do not know what B and A are, but you might be able to still connect them to this. Really cool property there. And that's where you can kind of actually just kind of build them and then measure and see if you can actually figure out what's the connection between them. Okay. And then question 2, this is your chance to try something. So you build yourself a triangle. And I want to talk through this one just a little bit because the directions aren't bad, but I gotta be honest, it's a little a little hard to follow at times, especially when it's all words. So here's the idea. You are going to build a large triangle. Okay. So build your triangle. Here it is. There's my large triangle. Okay. Now what you do is you're going to fold this side. So we'll call this A, up top is B, and over here is C. We're going to take point A, we're going to kind of fold it over so that when I crease right down from B down, I get a perfect 90-degree angle. Does that make sense? So you're going to fold the piece of paper, and the way, once you cut that triangle out, if you fold point A onto this side over here, you will make a 90-degree angle. Okay. So do that. That's what they're saying. Do that in order to get a 90-degree angle. And what you're really looking for is this point, which you'll have because you'll have this crease in the paper now. Okay. And we're going to call that point right there B prime. We don't even need this point really. We just used it temporarily to find this point right here. Now here comes the fun. Take B and fold it down, fold, and you'll have a crease like this, and fold it down on top. So now you'll have something that kind of looks like this. So again, this top point will now be touching down here. So kind of like a little origami almost. Okay, so this part up here is now gone. You've folded it over. Then take point C and fold it until it touches B prime, and take A and fold it until it touches B prime. And then you'll have a shape that looks like this. It actually looks like a rectangle. Okay. And if you think about it, that actually does show something about triangles that we should kind of know, because this angle right here will be right there. Angle C will be right here. And then we got angle B. Something interesting has just happened with this shape. So those are the two that I'd like you to try as group work. All right. Awesome. Thank you. I'll see you shortly. Off you go.